So, we had done several applications of magnetic forces on a charged particle. We started with uniform magnetic field and charge starting perpendicular to the field, then it goes in a circle, then if it is not perpendicular, then it goes in some kind of a helix or spiral. And we also talked of non-uniform magnetic fields, and then we talked of forces by the magnetic field on current elements, and from there the dipole moments and all those things. Now, in this series we will now discuss motion of a charged particle in combined and crossed electric field and magnetic field. So, crossed means they are perpendicular. So, we will have electric field, we will have magnetic field, and they will be perpendicular to each other, and then with some initial conditions on the particle's motion, we will see how it goes. So, that is the task today. So, suppose we have let us say we have magnetic field here and we have electric field here, or let us take magnetic field here and electric field here. This is our x axis, this is y axis, and this is z axis. So, what we are writing is that electric field E, which is supposed to be uniform, is magnitude and then j cap, and this field B is b k cap. And then there is a particle which moves, we will set some initial conditions, but this will be the thing. And the first condition, let me start with this: at t equal to 0, the particle with charge q, the particle charge is q, is at the origin and is at rest. And then onwards the fields will take over, right. So, at t equal to 0, the charged particle which has charge q is here, and at this instant it is at rest, and then see what happens, what these fields do. So, the magnetic field will not exert any force on the charge if the speed is 0, if it is at rest. Electric field will exert a force, and that force will be in the direction of the electric field, assuming q positive. So, it will start this way, this will exert a force that will create an acceleration, that will change the velocity. So, it starts this way, so it should start this way. But once it picks up velocity, then this magnetic field also is ready to exert force, and then this V cross B. So, V is in this direction and B is perpendicular to the board. So, V cross B will be towards that x axis. So, it will turn. So, it will start here and then it will turn like this, and it will gain speed, because as it goes up, it goes in the direction of the electric field and therefore electric force. So, positive work is done by the electric force on this particle. So, the kinetic energy will increase, and if the speed increases, the magnetic force changes, and therefore the curvature will be changed, and maybe at a certain instant the deflection because of the magnetic field is such that it makes a turn. So, this kind of motion is expected. Of course, it will not go below this plane, it will, the y will always be positive, that one can work out the algebra, we will do that. but this kind of motion is expected. So what happens here, and then does it reach here, does it go this way, does it go this way, does it go this way? Those are the things that we will write the equations and then see. Now extremely interesting method to do this is with crossed electric and magnetic field, that you change the frame. This is the lab frame from which we have described everything. Let us go to a different frame, some inertial frame of course, and this frame is, let us say, S lab frame. This is our lab frame S, and then we go to another frame, S prime frame, and this S prime frame is having axis parallel to these axes at t equal to 0. Origin also coincides. So it is the same figure, it is the same figure, these are all dash. So we are talking of S dash now, and with respect to this lab frame, this S is moving this way with a velocity v naught, with a velocity v naught, and this v naught we will choose very cleverly, this v naught will be E by B. Okay, E by B has dimensions of velocity. The force is Q and then E plus Q V cross B, right. So E and B have dimensions such that E and VB has same dimension. So E divided by B will have dimension of velocity. So we choose, the E is given constant, B is given constant, so E by B is constant. We choose this as the velocity of S prime with respect to S, and remember this origin is here, this axis is here, this axis is here, and so on, but this is at t equal to 0, and after that this will slide here and will go this way, this frame will go this way. So that is our S prime frame, that is our S prime frame, and in S prime frame, let us see what is the situation. In S prime frame, this is our X prime, this is Y prime, this is Z prime. So if this is velocity here V, then this V prime will be V and minus V naught t. Okay, V naught, V naught, V minus V naught. V naught is the frame velocity. In fact, this is a vector sign here, and this V naught is in this direction, so this is in I cap direction. So this will be the transformation. So here we have this V. So this V is equal to V prime and plus V naught I cap. This V here, I am writing this V, and the corresponding velocity in this is V prime, and V prime and V are related this way. Therefore, we can write V is equal to V prime plus V naught I cap. It is this. So let us see this force. We are talking in terms of Galilean transformations. So the frame velocity is small as compared to the speed of light. So under that I am writing this velocity transformation. So this force, and then in Galilean transformation the force remains the same. If you have two inertial frames, then the force remains the same in the two frames. So this F is equal to, which is now F dash in this frame, Q and E will be there, which is in fact E j cap. So I can write it E j cap plus V, plus this V is here, so it is V prime and plus V naught I cap, this, and then cross B. So cross B is B k cap, so it is B and then k cap. This is equal to Q E j cap plus V prime cross B. This is B, this is B, this is B. So I can write it V prime cross B and then plus V naught here, this V naught here, this B here, and I cap cross K cap. I cap cross K cap is minus J cap. And here comes the simplification. So this is, remember, V naught is E by B. So V naught times B. V naught times B is just this capital E. And so this becomes Q E j cap plus V prime cross B, and then plus this quantity is E. So E and then minus j cap. Alright, V naught is capital E by B. So V naught into capital B is capital E. V naught into capital B is capital E and minus j cap. And this E j cap cancels with this E minus j cap, and therefore force on the charged particle in this frame, in this S prime frame, is equal to Q V prime cross B prime B. This B is same as this B. We are just writing this expression again here, because we know that in Galilean transformation, when you go from one inertial frame to another inertial frame, the force remains the same. So force in S prime on particle is same as force in S. So this is the force in S prime also, and we want to write it in primed quantities. Therefore we are writing all these things. What we find is the force on the particle, net force on the particle is Q V prime cross B. What does it tell? You have a charged particle, you have a velocity, and the force is Q times velocity times magnetic field B. What does it mean? It means in this frame the electric field is 0. There is no electric field in this frame, only magnetic field B, same magnitude as this, same magnitude, same direction. So that magnetic field is imported here, but the electric field is not. The electric field becomes 0 in S prime. In S there was an electric field, but in S prime the electric field is 0. There was a magnetic field in S, and the same magnetic field is here in S prime, but electric field is not the same. It is E here and it is 0 here. So that great simplification comes with a great message also, that electric field is frame dependent, and similarly magnetic field is also frame dependent. In this particular case it is independent of the frames in S and S prime, but in general we have seen that in particular case electric field is not the same. It is E here, it is 0 here. There are situations, there are cases in which the magnetic field will meet the same fate. So electric field and magnetic field are not absolute quantities, they are frame dependent quantities. That is a great message from this. Now coming to solving the equation in S prime frame, now our task is very simple. We only have a magnetic field and then there is a charge and it has some velocity. What happens at t equal to 0? At t equal to 0, we are in S prime frame. At t equal to 0, what is the velocity of the particle? It is at rest here. At t equal to 0, the particle is at rest at this origin, and if you view from S prime, which is itself going towards right with respect to this S, if you view from there, this whole S frame together with this particle is going towards left. with a velocity of v naught, because s prime is going with a velocity of v naught towards right. So with respect to s prime, s is going towards left with the velocity v naught, and therefore in s prime frame at t equal to 0, the particle here is going towards left with a velocity v naught. So the particle has a velocity minus v naught I cap. So magnetic field in z direction, magnetic field is in z direction, and the particle is projected in I cap direction, negative I cap direction. So it is projected perpendicular to the magnetic field. So you have a uniform magnetic field, no electric field, and then you project a particle perpendicular to the magnetic field. What will it do? It will go in circle, right? We have done it several times. So it goes in circle. So I know what happens to this. I know what happens to this. If the initial velocity is in this direction, this is the initial velocity, and remember it's only magnetic field, this v naught is not going to change, the speed will remain v naught. The speed of the particle will remain v naught, and it will move in a circle this way or that way. Circle will be this way or circle will be that way. That we can work out from this v cross b. So this is velocity is in minus x direction and the magnetic field in z direction. So you can write that force at time t equal to 0. We are only writing that is q times the velocity is minus v naught I cap. This one is minus v naught I cap cross v cross b. B is bk cap. So this is q v cross b j cap. I cap cross k cap is minus j cap, right? I j k I. So k cross I will be j, but I cross k will be minus j. With this minus it will be this. The force will be in positive y direction. So the force will be in positive y direction. So it will go in a circle of this kind. It will go in a circle of this kind, this way, right? We have gotten the path in S prime frame, and it's a matter of transformation from S prime to S that we will get the path in our lab frame. But let's write x and y separately as a function of time. So in this case here, what happens at time t? You know all the characteristics of the center will be here, and this will be a radius, and how much will be the radius? We have calculated it mv by qb. So mv naught by qb, this will be the radius, and then it will have an angular velocity, and that angular velocity will be qb by m. All these things we had derived when we considered uniform magnetic field and then a particle projected perpendicular to it going in a circle. So these are the parameters. This r, you can see this r you can write as v naught by omega. This r you can write v naught by omega, qb by m is omega. So this is the kind of circle it is going, and in this is the radius, this is the radius. So in t time it will go here, and this angle will be omega t. At time t, the particle will be here. The particle will be here. It has turned through this omega t. Omega is the angular velocity, remember. Okay. So what is the x coordinate? What is the x coordinate at time t? This is the x coordinate. This is the x coordinate. And how much is this? This is radius capital R. This is angle omega t. So this is just r sine omega t. This length is r sine omega t, this length. So x is equal to minus r sine omega t. This is xy plane, x prime y prime plane. In this plane you have the circle. Okay, what is the y coordinate? This is the y coordinate. This is the y coordinate. This is x coordinate. This is x coordinate and this is y coordinate. How much is this? How much is this y coordinate? Y. Y is equal to this total r and then minus this total r and minus this much. This total r minus this much will be the y coordinate. In the direction of y, particle is here, so this is the y coordinate, this length is the y coordinate, and this length is this capital R minus this. And how much is this? This is this capital R cos of omega t. So this is minus r cos of omega t. So that is x prime and y prime. These are the coordinates of the particle at time t. Now what are the coordinates at time t in S frame, in the lab frame? What do we do? What do we do? We have this relation here, we have this relation here, we have V prime is equal to V and minus V naught. This is I cap, it is this. So this is dx, if I look for x component, say, so it is V prime x component, we are talking of x component, is equal to Vx component and minus V naught. This is x component. So dx prime dt is equal to dx dt and minus V naught. So we can just integrate and see that x prime is x minus V naught t. X prime is x minus V naught t. So you can write this, from here, this is x minus V naught t, x prime is x minus V naught t is equal to minus r sine omega t, and therefore x is equal to V naught t minus r sine omega t. You can further simplify it, V naught divided by omega times omega t here, and this r is V naught by omega, we had seen r is V naught by omega, so minus V naught by omega here, and then sine of omega t, and that is equal to V naught by omega and omega t minus sine omega t. We have got an x coordinate as a function of time. So let me write it here. X coordinate is V naught by omega and then in bracket omega t and minus sine omega t. What about y? What about y? You can do the same thing here. Y coordinate, y component. So V prime y is equal to Vy, V prime y equal to Vy, and this is 0, there is no y component here. So it is just this, and from here you can write dy prime dt, it's same as dy dt. So y prime is same as y, y prime is same as y, so y is just this, y is equal to, what is y? Y is just this, r minus r cos omega t, r you can take common, and r is V naught by omega, and then when you take r common, it is 1 minus cos omega t, so it is 1 minus cos omega t. So we have gotten the expression, the equations for x coordinate and y coordinate at time t. So we have solved this motion. Now our next question is, what is the shape of this path? What is the shape of this path? For that we need to do some calculus, right? We did say that it will start. We did say that it will start like this. We will say that it will start like this, something like this, right? This is our x axis, this is our y axis, the electric field is here and the magnetic field is in z direction. And from qualitative analysis we said that it will start like this, it will go somewhere. But the exact shape, for that we have to study these equations. This y is always greater than 0 first, because cos omega t is always less than 1, it is between 1 and minus 1. So this can never be negative. So this whole thing is above this x axis in this xy plane. So that is one observation. Then can y be 0? Can y become 0? Will the particle touch this x axis somewhere? So y can be 0. If y is 0, that means cos omega t is 1. So one thing is, yes, at t equal to 0, yes, at t equal to 0 cos 0 is 1, that is here. Next cos omega t is 1 if omega t is 2 pi. Omega t equal to 0 is 1, omega equal to 2 pi is the next time when this cos omega t will become 1. Cos of pi is minus 1, cos of 2 pi is plus 1. So at omega t equal to 2 pi, this is possible, y is equal to 0. And what will be the x there? X will be v naught by omega and omega t here. And if cos omega t is 1, then sin omega t must be 0. So that's it, v naught t. Omega t is 2 pi, so v naught into 2 pi, omega t is 2 pi, and then omega here. So you can write the, yes, it will go and touch here, there is some value, it will go and it will touch here. Next is, how does it touch here? Does it touch here like this? Does it touch here like this? In what fashion it is touching here? So for that you have to look at the slope dy dx. Okay, so maybe we will take from here. And then look at the slope, look at the dy dx. You can do homework, like from here you write dx. What is dx in terms of dt? Here write what is dy in terms of dt, and then divide and get this dy dt, dy dx, and then look at what the shape of that slope. So we will continue from here.